Hello everyone. So today we shall be continuing our discussion about the linear phase. So in the last class we had seen a linear phase system which is referred to those systems defined by the frequency response e raised to the power j omega is equal to modulus of this function times e raised to the power minus j omega alpha. Okay. So for the frequency response of this form, the phase of this function is entirely associated with the linear phase vector, which is this, and you have the argument of h e raised to the power j omega s minus omega times alpha, right? So now we shall, in the further discussion, we shall study some properties of this and of this linear phase vector, and these properties are studied generically. So we say it generalized linear phase. So a system is referred to as the generalized linear phase system if its frequency response can be expressed in the form which is given by where your alpha and beta are constants. Your this vector a of e raised to the power j omega, it's a real function of omega. So if we compute the phase of this system, the phase of this system is given by minus omega alpha plus beta, which is nothing but a straight line. And the group delay, let's denote it by tau of omega as grd of h e raised to the power j omega is given by minus derivative of the argument of h with respect to omega. So here we have this minus omega alpha plus beta which goes here, and finally we get this alpha which is constant. Okay. Let's see the other representation of this function, this one, to see when is it possible or what are the necessary conditions to have the generalized linear phase. So I can express this as e raised to the power j omega is equal to a e j of beta minus omega alpha, which in polar coordinates can be written as cos beta minus omega alpha plus j sine of beta minus omega alpha. Okay. So if the frequency domain, the time domain representation is given to us, that is h of n, then it could be also expressed this as summation for n minus infinity to infinity h of n e raised to the power minus j omega n, which again in polar coordinates can be expressed at the summation over n from minus infinity to infinity hn cos omega n minus j summation over n hn sin omega n. Okay, so here again hn is assumed to be real function. So if we compute the tangent of the phase angle of this function h of e raised to the power j omega, then it can be expressed as tan of beta minus omega alpha would be given as sine beta minus omega alpha by beta minus omega alpha. And by using the time domain function, it can be written as minus summation over n hn sine omega n divided by summation over n hn cos omega n. So from this expression, if we do the cross multiplication and combine the terms with with the use of some trigonometric identity, then this equation can be simplified to n is equal to minus infinity to infinity hn sine omega n minus alpha plus beta equals 0 for all omega. This is a very important equation. So this is a very important equation because this equation gives you a necessary condition on hn alpha and beta for the system to have constant group delay. But so this is a necessary condition. An additional thing to note that this is not a sufficient condition. We shall see a couple of examples in which we will give the sufficient conditions for the system to have constant group delay. Okay, right? So we can see a couple of examples. So class of examples of generalized linear phase systems. So for which, let's see, consider the example 1. Where we seeing this equation where we put beta is equal to 0 or pi. On alpha we have this condition that 2 alpha is equal to m, which is an integer, and on the function h we have h2 alpha minus n, which is equal to h of n. Okay, so let's see. So with beta is equal to 0 or pi, this above equation, this one, can be, it becomes the summation of n minus infinity to infinity hn sine omega n minus alpha, which is equal to 0. From which it can be shown that if 2 alpha is an integer, whatever be the terms you are having here, by opening this sinusoidal function, they can be paired so that each pair of term is identically 0 for all omega. So these conditions in turn imply that the corresponding frequency response has the form similar to this one, with beta is equal to 0, with beta is equal to 0 or pi, and most importantly that this function a of e raised to the power j omega is an even function and of course real function of omega. So let's write it down. So under these conditions, under this set of conditions, we have this one. We will obtain the frequency response as shown above with beta is equal to 0 and pi, and your a e raised to the power j omega be an even course real function of omega because of this condition. Now another example you can of generalized linear phase system, you can see when you have beta is equal to pi by 2 or 3 pi by 2, and still we have 2 alpha is equal to some m which is an integer, and the last condition we have h of 2 alpha minus n is equal to minus of hn. In the above we have positive hn, and here we have minus of n. Okay, so all these conditions imply once again that the frequency response has the would be of the generalized linear phase with beta is equal to pi by 2, of course, and in that case you would have a e raised to the power j omega, an odd function of omega. And for this case, if I apply these conditions to the necessary condition, it will become the summation over n minus infinity to infinity h of n cos omega n minus alpha is equal to 0, and it is satisfied for all omega. So these two sets of conditions what we have given in addition to this necessary conditions, they guarantee the generalized linear phase or constant group delay. But we have seen in previously in the last lecture in fact that there are other systems which satisfy this equation. The frequency response would be of this form, but they do not have any symmetricity condition, which you can notice from these two examples what we have given. So in these additional conditions, which are basically the sufficient conditions, here we have the symmetry. So both these conditions on Hn speaks about the symmetric conditions on Hn. Okay. Now in addition, here we have seen that the time index is varying from minus infinity to infinity. But now let's say we talk about the causal generalized linear phase system. So we are putting an additional conditions on the generalized linear phase system that they are causal. So it is pretty much straightforward that when we are talking about the causal system, so the summation what we have been considering in the inside the summation we had this Hn sine omega n minus alpha plus beta equals 0 for all omega. So earlier we had seen that this n varies from minus infinity to infinity, but if the system is causal, it will vary from 0 to infinity. So causality and the conditions which we had seen here and here imply that your Hn should be 0 for n less than 0 and n greater than m, where m is equal to 2 alpha is some integer. So what it says that the causal FIR systems, that is finite impulse response system, have generalized linear phase if they have impulse response of length m plus 1 and satisfy either of these equation sets, these equations. Right? Specifically, it can be shown for the first example, for the first set of conditions, that you can express h of n as h of m minus n for n lying between 0 to n, and it's 0 otherwise. Then you would have your h e raised to the power j omega as ae I just wrote AE that since it's an even function of e raised to the power j omega, and E would be minus j omega m by 2 since beta we have taken 0 for this case. So this AE is basically the real even periodic function of omega. Now similarly, if we have Hn as negative of Hm minus n for n lying between 0 to m and 0 otherwise, then you would have h of e raised to the power j omega as j times a naught and e raised to the power minus j omega m by 2, which you can express as a naught of e raised to the power j omega times e raised to the power minus j omega m by 2 plus j pi by 2. So it is clear that beta is pi by 2, where this function a naught is real odd periodic function of omega. Note that in both the cases the length of the impulse response is m plus 1 samples. Okay. So now we shall define 4 types of FIR generalized linear phase system in terms of the this impulse this h function like we have defined here. Okay, so we call them type 1 FIR linear system. So we will define 4 types. So the first one is type 1 FIR linear phase systems. And the idea behind defining these 4 types of FIR system, that the conditions which is basically this one or this one, they are sufficient to guarantee a system with generalized linear phase, but they are not the necessary conditions, right? So most of the time it depends on the type of symmetry or whether m is even or an odd integer, and this is for this reason we shall define 4 types of FIR linear phase system, where we discuss deeply about the type of symmetry and also whether the function whether the variable m is even or odd integer. Okay. So a type 1 system is defined as a system that has a symmetric impulse response. So in that case we have Hn is equal to h m minus n for n lying between 0 to m, with m is an even integer. Okay, so what it implies that the delay, which is m by 2, is an integer. And the frequency response is given by n is equal to 0 to m Hn e raised to the power minus j omega n. So if I apply this symmetric condition onto this summation, I will obtain h as e raised to the power minus j omega m by 2, and summation over k is equal to 0 to m by 2 ak cos omega k. I think you can derive this by yourself, where your ak coefficients are defined as your a of 0 as h m by 2 and your a of k as twice of h m by 2 minus k for k varying from 1 to up to m by 2. So from here we see that the frequency response is having the same the form which we had seen earlier, with beta is equal to either 0 or pi. So it is for this case. Okay. Now type 2 FIR linear phase systems. So it would again have the symmetric impulse response as we had seen above, but here the change is the variable m or the parameter m would be an odd integer. So in that case I am just writing the function directly. It is minus j omega m by 2 summation over k is equal to 1 to m plus 1 by 2 bk cos omega k minus 1 by 2, where your bk is this function 2h n plus 1 by 2 minus k for k 1 2 n plus 1 by 2, right? Again your h would have the same form with the time delay of m by 2, which in this case is an integer plus 1 half, and beta is either 0 or pi. Okay, so I think we can see directly a couple of examples, and over those figures I will write these functions for the type 3 and type 4. Okay, which gives you a clear idea about the symmetricity and about the parameter, whether it's even or odd. These functions you can derive by yourself also once you apply these conditions on the Fourier transform, sorry. So these are the four different types. So the first one is the type 1, where we had seen that m by 2 would be an integer and the symmetry would be around this point where we have beta is equal to 0 or pi. Now B figure is the type 2 FIR, is the impulse response of the type 2 linear phase system, where m by 2 plus 1 would be an integer. Okay, and here but you have the center of symmetry around this point, and the delay would be m by 2, no issue. Now for this type 3, this is type 3, the subfigure C, and it has the anti-symmetric impulse response, meaning to say you have Hn is equal to minus h of m minus n for n lying between 0 to m. Here m is an even integer, right? M is an even integer. So I will just write the expression, which you can also compute by yourself, as j bar minus j omega n by 2 summation over k is equal to 1 to m by 2 ck sine omega k. Okay, where your ck is twice of h m by 2 minus k. Here again k is 1 to m by 2, right? But you see the center of symmetry clearly. Type 4 is the figure D. Again you have m as an odd function, m is odd, and the impulse response, what you are seeing here, is anti-symmetric, right? So I will write directly the function h for the frequency response, which is h, just for your reference, j e raised to the power minus j omega m by 2, where you have summation from k is equal to 1 to m plus 1 by 2 dk sine of omega k minus 1 by 2. Okay, where your dk is given by 2h m plus 1 by 2 minus k. For k between 1 to m plus 1 by 2. Okay, as in the case of type 3 system, this function h would have the delay m by 2, which is an integer plus half, and beta would be pi by 2. So whenever you have this beta is equal to pi by 2 or 3 by 2, it would be anti-symmetric. When you have beta is equal to 0 and pi, it would be symmetric around the point of symmetry. Okay, so we shall carry forward this discussion with more couple of examples and going more deep into by discussing about the location of zeros. Okay, thank you.